from Boston University. David is currently a PhD student in Boston University. His advisor is Anusha Chandran, and he is working on several, let's say, topics in many-body localization, which is a topic that we know is becoming quite hot even here in IBS, PCS. I mean, we're also working on that. And today he's going to present the results of his last paper, which appeared around 1 month ago on Archive. And the title of the talk and also of the paper is Phenomenology of the Pre-Thermal Many-Body Localized Regime. David, I think you can start.
Great. Thank you for the introduction, Dario, and thank you for inviting me and having me here to present this work. So this is work done in collaboration with Phil Crowley at MIT and Vedika Kaimani at Stanford. And of course, my advisor, Anusha Chandran at Boston University. So what I'll be telling you today is about, is related to many-body localization, which is this story where very strongly disordered one-dimensional quantum systems have no transport. They don't conduct heat or charge, and they, in fact, do not even thermalize. So if you put some initial density profile of some atoms in one of these many-body localized systems, then unlike you're used to with an ideal gas or something expanding to fill its container, these atoms would just stay there and not move. And there are two kind of punchlines from this talk to take away if you want to stop paying attention after this slide. And the first of those is a result really not of the work that I'll be mostly talking about, but of recent results in the literature, which I'll just be summarizing, which is that MBL, many-body localization, as people usually discuss it in an asymptotic sense, in that is infinite system size, has not actually been observed in experiment or in numerics as of right now. And so I'll be explaining why I think that and why that's come out of recent results in the MBL literature. And it serves as a big part of the motivation for what our paper is about and what the rest of the talk will be about, which is asking how to describe the thing that people previously thought was MBL, but actually will thermalize very slowly. So that's something which we don't have great tools to describe at the moment. Really, everything that people have been studying in MBL is to describe MBL proper, this thing is actually asymptotically localized. But this thing which is slowly thermalizing, we don't yet have a good understanding of. And so this work is kind of building towards having a quantitative understanding of that pre-thermal many-body localized regime. Okay, so the outline of the talk, first of all, I'm going to introduce some background about localization and thermalization. I don't know how much of that will be new to anyone in this audience, but just in case. And then I'll summarize kind of the problems that have arisen in the MBL phase diagram in the last few years and why they have led to this vast revision in what people think about that phase diagram. And then I'll lead on to talking about pre-thermal MBL and our attempts to understand it. Okay, so I'll begin by talking just about localization in just a single particle context. So presumably everyone is aware that if you have a periodic potential and you place some electron in it, this electron will delocalize. All of the eigenstates in this periodic potential are these block waves. So an initial wave packet here will kind of spread ballistically throughout this periodic system. However, if I have a potential which is strongly inhomogeneous, either with random disorder, I'll usually be talking about, so like this scribble which I've drawn here, then instead if I put a wave packet here, it does not delocalize, it instead remains localized. So here are some example eigenstates that might be part of this system. They are exponentially localized around some potential minima. Maybe they kind of hybridize between some adjacent ones, but they are asymptotically far away. They decrease exponentially. And I want to kind of treat this as being a a contrast to thermalization. So the ergodic hypothesis in statistical mechanics says that if I start a generic system in some initial state, then under its own dynamics, it will kind of evolve and visit all microstates consistent with whatever conservation laws are in this system equally many times, right? So this is a system, this localized system is very much not ergodic, right? If I start an initial wave packet here, it does not visit all microstates equally many times. It only visits microstates where most of the weight of this particle is sitting around this potential minimum. Okay. Of course, you might say this system is not generic. It's not interacting. In any real system, there are, of course, many ways in which this particle could gain the energy it needs to kind of hop from this well to the next well and to the next well and kind of start diffusing throughout this system. One of those ways is by interacting with some background lattice. If there were phonons in this system, then they could deliver some energy to these localized electrons and let them kind of move around. And another way would be if these electrons had interactions between them, right? If this electron over here could deliver some energy to this one, then maybe it could allow this one to hop out of here and start moving around. And the story of many-body localization is that second mechanism, the interactions between these electrons, if they're sufficiently short-ranged, actually does not lead to localization. That if this to thermalization, so it remains localized. So if this inhomogeneous potential is kind of strongly enough disordered, and these interactions between these electrons are weak enough, and there are no like couplings to any kind of external environments, then these electrons should remain localized for all times, even in the infinite system size limit. Okay, so the kind of experiments that people do to explore this is they start with some inhomogeneous potential, which is here, and they load up some initial density of electrons. Actually, in these experiments, which I'm citing at the bottom, these are actually called atom systems, not electrons. But nonetheless, it's the same kind of story. They load up some atoms into this potential, and they load them up in some staggered pattern. So even sites have atoms in them, odd sites do not. If this system thermalized, you would expect this to relax to some uniform density, right? This is just like an ideal gas in some room you talk about in statistical mechanics. If you start all of your gas on one side of the room, it very quickly expands to fill everything. On the other hand, if the system were localized, then there should be some residual imbalance between the even and odd sublattices. So here we can see that there's some extra atoms on the even sublattice as compared to the odd sublattice. So there's some memory of the initial condition that you started your system in. And this is described phenomenologically through some local integrals of motion. Basically, you say that there's some kind of conserved charge sitting at this site, and this initial density of atoms had some overlap with that conserved charge, and that means that it can't spread out because that charge, of course, is constant in time. People do measurements of these imbalance ratios, and they can see that indeed, if you have no disorder, that's this bottom line, then this imbalance ratio quickly relaxes to 0. Whereas if you have strong disorder, then on the kind of numerical timescales, you can see you get some residual finite value, which is to do with this conserved charge, this memory of the initial condition. Okay, but I've been showing experimental data. What has really driven the field forward in the last few decades has been access to kind of large-scale numerics. So here I'm showing a plot from a paper by David Luiz and co-authors, and on the vertical axis, there is some energy density in some Hamiltonian system. And on the x-axis is disorder strength, which I'm going to call W throughout this talk. And so in this phase diagram, maybe you don't need to pay attention to all the specific quantities that are being plotted, just to the labels, ergodic MBL. There's some ergodic phase where things thermalize very well. here in purple, and there's a many-body localized phase, which is in orange. And there's some transition between them, which at kind of in the middle of the spectrum at energy densities corresponding to infinite temperature, there's a critical value, which is estimated to be about like 3.5 or around there. But this so later on, I'm going to explain that this actually was not the complete picture. There are problems with this diagram as I presented it, but this was the picture that people had kind of before around 2019. So here's the phase diagram. I'm only going to draw them being one-dimensional, which you can imagine is like this cut in the previous phase diagram, which I showed. The model, which you should have in mind, is this disordered Heisenberg model, which is what I'm mostly going to quote numbers for. It has Heisenberg interactions, so it's a spin lattice model in 1D. It has Heisenberg interactions between nearest neighbor spins, and then an on-site magnetic field along the Z direction, where the magnetic field strength is chosen randomly from some interval from -W to W. So W tells you like how much these magnetic fields can vary.
How is this model related to the many-body problem?
So this is a many-body problem. Like I can rephrase this through a Jordan-Wigner transformation in terms of fermions, where like an upspin would be like the presence of a fermion. And in that language, this is a disordered type binding model with nearest neighbor density interactions. Okay. Yeah, so this WC is in that language is some on-site potential for these electrons. Okay, so here is what the phase diagram looked like before 2019. There's some well-thermalizing phase on the far left, where things quickly lose memory of their initial conditions. There's some transition, which people put to be around 3.5 or so in units where the coefficient of this coupling is 1. And then beyond that, there's some many-body localized phase, in which there's memory of initial conditions. And okay, maybe you can be more pessimistic. There's some like finite size scaling with L, but people didn't estimate that finite size scaling as resulting in the critical transition disorder strength going above around 6 or 7, right? Certainly not going to be 10 or something. And in the infinite size limit, they'd expect there to be a thermal phase, a sharp transition, and then an MBL phase. And really the kind of critical region around this transition point should be governed by so-called rare region effects. So the idea is that physics here is dominated by rare parts of your disorder realization, your inhomogeneous potential, where you just happened to have less disorder. It was almost periodic or something. On this side, sorry. So on this side, you just happen to find a region with less disorder. So this is like a rare region which looks thermal. And that's meant to control the dynamics here. And on the other side, you sometimes pick extremely inhomogeneous potentials, and something looks localized, even though really it is thermalizing in the infinite size limit. Okay, but there were problems with this picture. As I said, like it's had to see substantial revision recently, and I will kind of enumerate what some of those problems were. So on this side of the transition, I just said like there's meant to be these rare regions which govern the physics here, but actually people don't see them. So you would expect here, if there were these rare regions governing the dynamics, then there should be a very broad distribution of like transport coefficients in different samples, right? As you sometimes select regions sometimes select samples which are very strongly disordered, and sometimes you select samples which look thermal. You'd expect to sometimes get like higher conductivities and sometimes get low conductivities, but people don't see that. They see most samples have about the same kind of conductivity. Furthermore, when people look at like a thermalization time, the time it takes to thermalize, they see that this thing is actually increasing exponentially in the disorder strength, which is really fast, but they don't actually see it diverge. So it does increase very quickly, but they can't see it like hit some asymptote. Okay, so that's a sign that there's actually no transition here. Furthermore, another sign that there's no transition here, when people look at critical exponents for like the divergence of the correlation length, in 1D disordered systems, like randomly disordered systems, there's some general bounds on what those can be. They have to be at least 2, and people measure them to be 1. So that's not allowed. There has to be some kind of problem here. There's some like extremely strong finite size effects. And those are also manifesting in what people estimate to be the critical disorder strength at different system sizes. They see that actually increase linearly in system size. So in this infinite size limit, people never see really clear convergence of this quality. And then the thing that really, the straw that broke the camel's back and like really convinced people that really this phase diagram has to change was when Morningstar and co-authors and follow-up paper by Dries Sells found that actually there aren't any quasi-local integrals of motion in this regime that people were looking at. So there's none of these things which would ensure memory of the initial state. These things actually are not localized enough to be stable in these regions. Okay.
Sorry, it's not the focus of your talk, but can you give us a glimpse of how one can see that there are no quasi-local integrals of motion? Or maybe we can postpone to the discussion later, I mean, if you want.
Sure. I mean, it was really a numerical result, right? So they had some clever, I mentioned that there's this rare region physics. Yeah. So that's some instability of MBL. And basically they looked at heating rates, like if they attached a rare region that was basically thermal to the end of their chain, can it, like does the heating rate of like distant spins decrease fast enough for this spin to not be affected by this rare region? And basically they found like wherever they could do numerics, it doesn't. Like it heats quickly enough to thermalize the entire chain in principle.
Okay, thanks.
No worries. Okay, so this had to change a lot. Kind of more recently, the phase diagram started to look like this. So there's still some thermal region, a very small disorder. If there's a transition, it has to be at least W of like 20. Right, and it could well be very much more. It could be 50, 100. There's a not insignificant camp of people who are now saying that it's an infinity, that there's no MBL at all. But so I mean that's yeah.
Could WC actually be infinite, and can one try to fit the results to a fixed point at W equals infinity?
I think all the current numerics are consistent with WC being infinity. And I mean, like it could be infinity. There's this proof by John Embry that basically that it's not infinity. But I mean, I guess if I had to summarize the status of that proof, it seems to be like not airtight enough for the mathematics community to really put their weight behind it. And it's not simple enough for the physics community to see that it's obviously correct. So it's somewhat, it's not convincing to the people who say that WC is infinity.
Sorry, related to that, because I remember at the moment, I mean, let's say before 2019, especially let's say Fabiana Lé, and I mean, they were emphasizing that MBL is not Fock space localization. They were saying, no, states are still not Fock space localized, but yet you are already in MBL. Now, what you, or let's say most people call MBL is Fock space localization, or this is not yet super clear?
I think it's still not required. Like the thing that people were probing to say that WC has to be at least this big was not Fock space localization.
Okay.
But I think that like the people who say that WC is like bigger than infinity, they would basically say that what people see in finite size numerics as MBL is basically Fock space localization.
I see.
And they're saying that like that was like they just got to large enough disorder that the disorder exceeded their many body bandwidth, and they had Fock space localization.
Okay.
And then, but then below that, they thermalize. So, but I think the people who still believe like WC is finite still believe that you shouldn't need Fock space localization to see MBL.
Okay, thanks.
No worries. Okay, so there's still meant to be rare region effects around this critical point, wherever it is. But that critical point is no longer close to where people were studying before. So that's good. There's no reason to expect rare region effects over here. And indeed, they're not present. And so like the location of this critical point is still open, and it's still an interesting question. But there's kind of a more immediate question, which is how do we understand this huge yellow region that got opened up by moving this critical point, right? This is something that people looked at. Yes.
Maybe I should shut up until you finish. It is this pre-thermal MBL is sharply defined or not? No. With respect to the thermal one.
Yeah, so it's a crossover regime.
Okay.
It's So there's I mean, like I'll make some like characterizations of it, but no, like it's not sharp, right?
Okay.
This is some like regime which I'm kind of shading, and like it'll have some properties, but it only crosses over into something which is quickly thermalizing.
Okay, thanks.
Right. So there has opened up this large regime, which people previously thought was many-body localized, but actually does thermalize extremely slowly. And so to some extent, we can understand what's happening here as just being many-body localization until eventually you thermalize. So if you want to understand things well before the thermalization time, you just pretend it's many-body localized, and that tells you everything you want to know. But there are more questions that we want to know about this regime, now that we know that it really does thermalize. And that is really like, why does it thermalize? What is the instability here that is causing it to eventually lose all memory of its initial state? And how does it do so? And ideally, we would understand also why it's so slow and why it takes so long for this stuff to thermalize. Okay, so that's going to be the rest of the talk and the topic of our paper, talking about like this pre-thermal MBL regime and how we can understand it and what it does. And so to kind of begin that discussion, I'm going to share a few like kind of numerical observations about this regime that we might try to explain with some theory.
So start on that. May I ask another question? The Heisenberg model that you write is like the spin Heisenberg model with a random field in one direction. I can apply to it the Imre-Ma argument for the random field systems, and that would tell you that the Z component of the spins will not order because of the Imre-Ma-like domains, but the transverse X and Y components could order in 2 dimensions and higher, but will not order in 1 dimension. So doesn't the Imre-Ma argument kill any phase transition at finite W here?
I'm not familiar with the Imre-Ma argument in this context.
The Imre-Ma argument simply says that the random fields Hj have a distribution. So if you take a finite domain, you can find finite domains in which the Hj's are such that you might order within that domain, because the Hj are not very large within that domain, but the domains win eventually, and there is no long-range order in low dimensions. You have a competition between the surface energy of those domains and the bulk within that domain. The bulk is dominated by the Hj's and their sum, and the surface to bulk ratio depends on the dimension. So in 1 dimension, the domains win. And
right. This sounds like a, yeah, why I haven't encountered that in this context before. I think the reason I haven't encountered it is it sounds like an equilibrium argument, right? This is all that, remember I said I was working like in the middle of the spectrum. So this is all effectively like infinite temperature, right? Like these like kind of statistical mechanical arguments about free energy don't clearly apply to these kinds of systems. Like if MBL is real, they shouldn't apply. Maybe we can talk more afterwards if I haven't understood. Okay, so numerical observations about pre-thermal Mbl. First of all, it's really slow. So I'm going to use tau in this talk for the thermalization time. In this thermal phase, tau is like on the order of the local bandwidth, which I'm just setting to 1. So it's on the order of 1. And then in this pre-thermal Mbl phase, it increases exponentially, right? So I'm going to say log tau is order W, right? So it increases like a lot. And if there's later on some real Mbl phase, tau should be strictly infinity. You never thermalize. Okay, so that's one of the observations we can make, that log tau increases linearly in W. Another thing that we can see, which is maybe more a hint towards method than physics, is that the eigenstates in this regime change a lot with system size. So when you're looking at small system sizes, your eigenstates look, as Dario was saying, basically Fock space localized. They look like they're basically just product states. But then when you increase system size, all of this stuff is thermal. All the eigenstates here should satisfy the eigenstate thermalization hypothesis, which is to say that they look random in your product basis. So they start to like go, they start to have like huge changes in what they look like.
Maybe
so
I will just ask, can I ask one question? Yeah.
Mm-hmm.
So what kind of physical quantity you are using to derive this thermalization time?
We'll be looking at autocorrelators of just like single spin relaxation.
So how that kind of physical quantity will be different from something other quantity, like for example spectral form factor? That also gives some idea about this thermalization time, right? So how these two thermalization time could be similar or different, because this is two kind of different kind of curve. So one is you having spin correlation, and then this is another.
Right. I mean, they should be, yes. So they should be closely related. I certainly expect their scale, like any thermalization time you define either through like spectral form factor or just looking at autocorrelators to give you the same scaling with W at the very least. I kind of prefer autocorrelation functions because they do relate to what people can measure in experiment as opposed to the spectral form factor. But both of these I expect to give you similar estimates for tau, or at least for log tau, which is less sensitive.
Yeah, David, if I remember correctly, the relation between the two is as you said, is rather close in the sense that the spectral form factor is like, I mean, it's very close to be like a 2-point function in which when you compute the 2-point function, you have also, let's say, you have the matrix element of right, and essentially you which is not really the interesting part for thermalization, because that is something that is time independent. The spectrum form factor more or less factor out that contribution. So morally, they are really the same thing. I think you are right. Yeah.
Yeah. I see. Yeah. Good.
Okay. So the last observation is about these autocorrelators, which I'm defining in this way. So this order averaged trace of just ZZ autocorrelators, and we see that they decay like a stretched exponential, which is this functional form here. Okay.
Sorry, Z is the. I'm a bit confused. What is Z? Maybe I'm.
This can really be any function which is composed of like sigma z operators. Right?
Okay.
So it could be imbalanced, it could be local, like sigma z.
Okay, good. Yeah, thanks.
Yeah, we predict all such things to behave like a stretch exponential. Okay, and this is what we're going to, basically our theory is going to be a theory of like autocorrelators, right? We're going to be able to predict, well, okay, maybe that's wrong. That's like the main output of our theory. We're going to have some method which is based on the Jacobi algorithm for diagonalizing matrix, and it spits out that this autocorrelator should be a stretched exponential, and it can even tell you what this value of beta is going to be from some independent numerical experiment. Okay, so that's what we're going to build towards, a prediction of C of t using this Jacobi method. Okay, so here is a plot of those C of t's versus time on the x-axis on a log scale at some system size. Not in the Heisenberg model, actually, in a different model, but kind of unimportant. They all show similar behavior. And you can see that as I increase this order, W, these curves kind of stretch out a lot more. Their timescales go up exponentially. And I have here in red dashed lines some stretched exponential fits to a few of these curves. And you can see they really capture the behavior in like all different regimes, or at least many different regimes. Okay, and if I plot the fit parameters that I get out of those stretched exponential fits, I see that tau, the thermalization time, or at least this local relaxation time, indeed increases exponentially with W, and the stretch exponent beta does something with W, decreases. But we don't understand if there's some kind of universal form for that yet. It doesn't appear to be. Okay. So maybe another clue that can inform what kind of theory we should be looking at is that the variation between like individual correlators that we look at in like different initial states seems to have more variation than when we look at different disorder realizations, right? So this is more on the theme of rare regions not being important. We can pick any like kind of particular disorder realization that we want. And then most of our variation seems to come from different initial states in this trace rather than averaging over different disorder realizations, right? So here are some different initial states which are displaced vertically. So the zero line for each of these curves is along the dashed line of the same color. X-axis is time. Y-axis is this correlator in a particular initial state, all with the same disorder realization, but randomly chosen initial states. And you can see that each of these curves can do quite different things, right? So this teal curve seems to be decaying to zero with some oscillations on top. This red curve is oscillating around some non-zero constant pretty quickly. This green curve seems to have some residual value, at least on these timescales. This blue curve has some like much longer oscillations around zero or thereabouts. And these I want to identify as like Rabi oscillations, right? So this is, I'm going to argue that this is a kind of resonance effect. Okay,
so yes,
but this is,
okay. So
yes.
I have just one question. So I just bit confused because what is this operator sigma subscript 0? What it means? I mean, what is the subscript?
Oh, sorry.
0
So this is just the spin operator at site 0. So it's periodic boundary conditions. So 0 is unimportant. But the Z component, so the part that would be conserved in the W to infinity limit.
So you are considering periodic
yeah, and then
boundary
scaled to
condition,
it starts
right?
at 1. Sorry?
So you are using periodic boundary condition, right?
Yes.
So then what about if you start with middle of the kind of system? The correlation between the spin in the middle of the chain.
Sure. With open boundaries, it would look the same. Like these times are too short for you to be able to see the boundary conditions at these system sizes. So I would expect it to look very much the same in open boundaries at the middle of the chain.
Okay. Yeah.
Okay. Okay, so we can assemble these clues. Let me just summarize them. So whatever's accounting for this slow decay, it's not rare regions, right? The variation we see is mostly state to state, not sample to sample. So if we're looking for a theory of this regime, probably we should be focusing more on what states do as opposed to what particular samples do. Somewhat contrary to that, I think that one should not look at eigenstates in this regime, right? They have these extremely strong finite size dependencies. And in this infinite system size limit, they're all going to satisfy the eigenstate thermalization hypothesis. So they're going to look random. Of course, they account for all dynamics in the system. If you know all the eigenstates precisely, then you know everything. But it's difficult to predict what those eigenstates will look like. For instance, these kind of finite time, yes?
Yeah, how do you see that they satisfy ATH? I mean, I thought that is quite hard, right? Because to see that they satisfy ATH, you need to go really to large N. Otherwise, or
right. So
let's
no, I haven't seen it numerically. I'm saying that the self-consistency arguments for MBL fail in this regime. So I expect it to thermalize. And then if I accept that the eigenstate thermalization hypothesis is true, this means that the eigenstates should look random.
Okay. So it's not something that one can actually see with the current numerics. Okay, good. Yeah. Okay, thanks.
No worries. Okay, but like in the eigenstate thermalization hypothesis, like how finite time dynamics is encoded is in some correlation between like level spacings and like matrix elements of eigenstates. And that's difficult to predict, right? Like I can't take a microscopic model and just tell you what that's going to be. And that's really because the eigenstates fundamentally are working at the wrong time scale. They're like infinite time objects, whereas the questions which I'm trying to ask are all about finite time, right? I'm asking about like, well, how do I approach thermalization? Whereas the eigenstate is really telling me you're thermal. So it's like stuff that's like way out here, whereas I want to know all this. Okay. So, and then the other lesson that we take away from those initial state plots, which I plotted, is that we want to have a description in terms of resonances, right? Like I identified this kind of Rabi oscillation in one of the plots, which I identify as a resonance effect. And there's been like many other works in the literature recently, which have kind of pointed to this being really important. Some kind of resonance in between states in this MBL regime. But most of these papers, which I'm citing down the bottom here, have been talking about resonances in eigenstates, right? They've been looking like really deep in the MBL regime. And they're saying, well, my eigenstates are going to be like product states most of the time, but sometimes they look like cap states between like one product state and like the other product state or some other product state. And this is what they call a resonance. Our eigenstates are not going to look like that. Our eigenstates are all going to look thermal. And so we need to try and make sense of what we mean by a resonance at finite time. And the tool that we use to do that, and as a numerical tool as well, is this Jacobi method for matrix diagonalization, which will be able to relate to kind of a finite time notion of resonance between states, which will be able to tell us that we've got these spins flipping in time, and allow us to build up to these curves based on a resonance picture. Okay, so what is the Jacobi method? It is an iterative process to diagonalize some Hamiltonian. So here, this gray block is my Hamiltonian. And the algorithm is to first identify the largest off-diagonal element, which I've highlighted in red. This matrix is Hermitian. So if this is some largest element in absolute value, then there's an equal one on the other side. And the Jacobi algorithm says that you should try and diagonalize just the 2x2 block formed by this element and the diagonal elements in its row and column. Okay, so you conjugate this H by some rotation R0, R0, which is going to affect all these elements which I've highlighted in blue. And you choose this R0 such that what previously was the largest element becomes 0. Right, so you diagonalize just that block. And so I'm going to say that you decimate this element, right? So there's some decimated element here in kind of renormalization group language. Unlike renormalization group, you don't then forget that this row exists or this element exists. You keep it around and it could become non-zero later again. And then you repeat. So you find the next largest element, you decimate that, you find the next, you decimate that, and so on and so forth. And eventually you find that this diagonalizes the matrix. So on the left-hand side here, I'm plotting the decimated element versus the number of rotations that you do. And you can see that at all different disorder values in the Heisenberg model, the maximum element decreases. This is showing that you're like moving towards being diagonal. Doesn't decrease monotonically. It can have like little spikes, but those are mostly irrelevant. Overall, it does decrease. Kind of the more useful plot is this one on the right, the one that we like more use, which is a histogram of all the decimated elements. Yeah, so on the vertical axis is like some distribution, and on the y and on the horizontal axis is the size of this decimated element. And what I want you to notice is that there's this extremely broad power law distribution of decimated elements, right? So this should be regarded as a distribution of timescales, right? So Hamiltonian elements give like frequencies. So this is saying if we can relate each of these timescales to some kind of resonance process, then this is saying that these resonance processes are all broadly distributed in this kind of power law way. And once you have these broad power law distributions, it's not so hard to get stretched exponentials out, as I will argue.
I have a couple of questions. The first one is how can I be sure that this thing converge? Because as you said, after an iteration, in the second iteration, you can modify again that element. So how can I be sure that somehow this?
Sure. I mean, again, this isn't controversial. It's been proved in the 1800s when Jacobi first proposed the algorithm. How you see it is that you think about the norm of the off diagonal. So when you do this rotation, which conjugates this matrix, it preserves the norm of the entire matrix, right? But it takes the norm from this element and it puts it into the diagonal, right? Every other element that was affected just gets is norm preserved, right? You just take cosine of this thing plus sine of that thing. You put it here and you do the same thing over here. So none of the norms of these other places gets changed, but you do remove some norm from the off diagonal by taking this element and putting it in here. So the norm strictly decreases as you do this, and so you can prove convergence. And yeah, it has the same kind of scaling as other matrix diagonalization techniques. It's n cubed floating point operations. Full diagonalized matrix.
I see. Okay. Sorry, can you explain a little bit again what you are representing on the right plot in the next slide, because I lost. So here yeah, please.
Basically, I just took all the data points in this left plot, and then I histogrammed them, and then I plotted them on a log scale.
I see. Okay.
So this is a density.
Okay, thanks.
Okay, so that was some distribution of timescales. Now, how do we make sense of these things being related to resonances? So the idea is to look at these rotation matrices. So I could parameterize them in this way in terms of some rotation angle, eta. And if I look at this distribution of eta, here's just another histogram of eta versus P of eta versus eta. And you can see that most of the rotations I do really don't do very much at all, right? The kind of overwhelming majority are extremely close to the identity. Then there's some rotations which actually do quite a lot, which take me from a state where it was whatever my initial basis states were, and then produce a catch state, basically. They go from like a sigma z eigenstate to like a sigma x in this 2x2 block of many-body states. So at some kind of naive level of analysis, which turns out to be sufficient for many purposes, I could kind of approximate this whole distribution of etas as just being two delta functions. Just say either I do nothing, I just take my initial many-body state and I just leave it alone, or I make some kind of resonance, right? I take my initial many-body state and I hybridize it kind of equally with some other many-body state. And Phil and Anusha, co-authors on this work, have like explored like the efficacy of this approximation in other contexts, and they find that it works pretty well for certain quantities, which is basically disorder averaged, or rather state averaged quantities. This works fine. Okay, so this is the kind of thing I want to identify as a resonance. And now notice that this notion of resonance has a time scale attached to it, right? Because this rotation occurred because I decimated some Hamiltonian element, and that Hamiltonian element is telling me a frequency. So this is a notion of saying that like I've got this resonance, and it's really occurring at a particular time, right? So it's like a finite time resolution of what is a resonance. Okay, yeah, so that's what I was just saying, that like I want to identify like things where I don't do anything at a particular time scale with these kinds of states in green, which really are not relaxing. So you imagine that like my Hamiltonian in this basis basically looks just like a sigma z Hamiltonian, right? And I started in an initial sigma z eigen state, and so I just stay there. Whereas this other one, where I had to do some large rotation in this basis, or for this state, my Hamiltonian originally looked something like sigma x. That's why I had to do this large rotation to make it diagonal. And so if I initialize in a sigma z eigenstate in this sigma x Hamiltonian, I'm going to process. And that's what this is. This is this precession manifesting as some oscillation in the sigma z expectation, or in the correlator in this case. Okay, so I want to like identify these things as being like these states, and these resonances as being these oscillatory states. Okay, so somewhat schematically, that the ingredients that we have is we have this broad distribution of timescales. We have this notion that some of these rotations, some of these timescales relate to resonances, some of them do nothing, and we understand what those resonances do in terms of like actual correlators. So we like take all these ingredients together. And we can predict what is the autocorrelator. Somewhat less schematically, what you actually do is you take your Hamiltonian, you run Jacobi on it until some time scale of interest. It doesn't have to be infinite time. You just stop whenever like you've captured like as much as you want, and then you do some approximation to the correlator in this form. So this looks a lot like the Lehman representation for the autocorrelator in eigenstates, but actually I'm not using eigenstates. I'm using just whatever states the Jacobi algorithm has told me to use, which is I'm writing here as A and B, which means that there's going to be some error on this, which is well controlled, and goes like t on tau, whatever time scale you're going to squared. Yeah, and there are like more precise estimates for what this should be. Okay, so what does the correlator look like? It's got some matrix element term, which basically is going to function to pick out resonances, right? This is only going to be large enough diagonal matrix elements when you've done a resonance, right? That's when you've got these kind of sigma x elements. And it's got some time scale here, which you can work out from this distribution of Jacobi timescales, this very broad power law. Okay, so yeah, you make some assumptions on this, which basically encode what I just said, that you can work out this thing through resonances, and that this thing also is controlled by resonances. And the result that you get is stretched exponential decay for this C of t, with some thermalization time, which is it's the log of something. Like you can argue it's order W, but you might recall from the previous plot I showed you of log tau that it really was just like a straight line. We would more say that like it should have like a straight line part, and like maybe it could diverge. So it's somewhat surprising from our analysis that it's such a good line. But what is less surprising from our analysis, and something that we can check, is that this stretch exponent here really comes from this distribution of this histogram of the elements that you decimate, right? So there was this broad power law distribution. That power law exponent is the exponent that shows up in this correlator, right? So that means that we can do a test of our theory, right? We can look at the output we get from Jacobi, and we can measure this power law, which we say should be of this form, and we extract whatever this theta is. And then we can independently go and do real-time dynamics in the same model, and try and fit a stretched exponential, and we can extract this stretch exponent, beta, and our model of dynamics through resonances predicts that this beta should be minus theta, right? So we can check that in various models. So here on the vertical axis, I'm plotting this stretch exponent from dynamics, beta. On the x-axis, I'm plotting this exponent turning up in this histogram, this resonance exponent. And I have onto this dashed line the theoretical prediction that beta is minus theta, and each of these different colors is different disorder values in 3 different models of the people used to study MBL. 2 Floquet models and 1 is the Heisenberg model. Okay, and you can see that agreement is, I guess, what I would describe as good. It's not perfect. It might have been a bit suspicious if it was perfect, given that we made some approximations in this argument. But I think it's kind of compelling enough to indicate that we're on the right track, that things really are progressing here because of resonances, and that you can understand these resonances through this Jacobi method. Kind of like this finite time resolution of when resonances start to form. So we're using actually not all our own data, but we fit these stretch exponents to results that are already in the literature in these 2 papers. Okay, so to summarize, kind of recent results in MBL indicate that the phase diagram needs to be substantially revised, and nowadays it probably should look more like this, where there's some well-thermalizing regime and then an extremely broad, also thermalizing regime, but which thermalizes extremely slowly, which we're calling Pre-Thermal Mbl. And then maybe that there's a crossover, so there's a sharp transition to an actual MBL phase at much stronger disorder strength. But again, like some people debate whether or not this is actually present. Furthermore, in this pre-thermal MBL regime, you can understand dynamics as arising through many-body resonances between different states. And you can use this Jacobi method to like numerically get at these resonances, and also to kind of have an analytical framework to understand what you mean by a resonance, like when it's not in an eigenstate. Okay, so in terms of outlook for this work, so we developed like this new tool, this Jacobi method, or at least, I mean, it's not new, of course, it's named after Jacobi. It was figured out in the 1800s. But the application to dynamics is new. And we think that actually you could apply this to many other dynamical systems than just MBL. So any kind of system which looks basically like this, where you have some like well-thermalizing regime, then some slowly thermalizing regime, and then like it's not even important whether or not there's actually a crossover to something which is not thermalizing at all as a function of some tuning parameter. So for instance, you could look at it in other strongly disordered systems which are not strictly speaking MBL, such as strongly disordered systems in higher dimensions, or with long-range interactions. And I guess I didn't write it here, but also everything that I've said should work just exactly the same for quasi-periodic disorder as opposed to random. So everything should just, the description in terms of resonances and even its broad distribution should just be exactly the same. You could think about it also in systems without disorder, but which nonetheless thermalize slowly. So we've actually already started working on like Floquet pre-thermalization. So like if you have very high frequency driving, you also don't thermalize very quickly. People a few years ago were talking about translationally invariant MBL. They eventually decided that MBL in this context doesn't exist in an asymptotic sense, but nonetheless, they saw things that look a lot like MBL. So maybe that could be this pre-thermal MBL, and maybe it could be understood using Jacobi. Or close to integrability, you also have some remnant of this integrability preventing you from thermalizing very quickly. And maybe even there, you could apply Jacobi, with that one kind of more speculative. What we're talking about should also apply and like work really well on random regular graphs, like Anderson models on random regular graphs, which people have used as like a Fox-based model for MBL before. So we think that this Jacobi method will work really well there. Maybe even in dissipative systems. Again, this is kind of more speculative, whether or not you can use Jacobi even in an open system. And based on like the work in your group, I know that you've been looking at this master formed SYK model. Maybe that could also be have Jacobi applied to it. So basically, like we have this new hammer, and like we're somewhat like looking for nails, things which Jacobi could work well to address. So here is the man himself, Jacobi. Okay, so that's the end of the talk. I'd like to thank Phil Crowley at MIT, Vedika Kimani at Stanford, and of course my advisor Anusha, as well as our various funding sources and Boston University. All right, thank you. I'm happy to take any more questions.
Yep. Okay, thank you very much.
How depends on W?
What was that?
How does tau depend on W?
It depends on what regime you're looking at, but I think I have it somewhere. Exponentially, basically. So in this kind of thermal regime, it's set basically just by like Fermi's golden rule.
Eventually meaning it diverges at W equals infinity.
So if it's exponential all the way, then
right.
Yes.
But you see no deviations from that exponential.
No one has seen deviations from that exponential. No one has seen signs that this thing is going to asymptote at some finite value. But like I should say, like they are like very limited by system size and by time scale. Like if this divergence had to happen at like people now have bounds at this thing being like 20, like you'd never be able to measure the thermalization time there. It's already like far longer than like certainly than the lifetime of any experiment, right? So it becomes kind of a completely theoretical point.
There is no size dependence on the relation between tau and W.
So this is meant to be the like converged value. Like of course, like if your size is small enough that like your Heisenberg time even cuts off the evolution, then you're never going to. Then basically, okay, let me say it clearer. If tau is longer than the Heisenberg time, like 2 to the L, then you're basically going to measure tau as being infinity, right? You're going to see localization just because your Heisenberg time came and cut off evolution before you could hit the thermalization time. Okay, but once your Heisenberg time and like all your like kind of various modes have exceeded tau, then you should be able to see that tau has some fixed value which is independent of system size.
Okay.
Do you think? No, right? I mean, do you think some, let's say, spin-off of this method could be of any use to provide, how can I say, alternative routes toward a proof beyond, beyond Mbl, let's say. Do you think there is anything that could be used to provide the proof of the final?
Yes, I do think that. So the kind of part of the reason why I think that is that John Embry's proof actually does use the Jacobi algorithm in various disguises. Like maybe not exactly. It's more like some like Schrieffer-Wolff transformation, which he does iteratively. He variously compares it to like a kind of block version of Jacobi or Schrieffer-Wolff or KAM. Mm-hmm. But he has, for instance, a single particle companion to his MBL piece, where it really is just Jacobi. So yes, I think that if we had like a much more kind of quantitative and precise understanding of this algorithm and of its convergence in like extremely large matrices, then we could have an alternative proof towards an alternative proof of MBL. Or maybe just a better understanding of John Embry's proof. Yeah, kind of like a simpler phrasing of it, which is more accessible. Or maybe we discover that there's some problem. I don't know. But yes, I do think that there's room for like analytical control in this algorithm that you can really make progress on the pure theory side, pen and paper.
Sorry, I have a simple question. So you mentioned, well, more like a clarification. Could you, you mentioned in the conclusions that translationally invariant MBL doesn't exist in the asymptotic sense. Could you, expand that a bit?
Sure. So the story with this translationally invariant MBL was meant to be that you picture it like a real crystal, right? Like there's some heavy particles, which are like atoms, and they're basically frozen, or like they have some like initial disorder. You treat them as static. So you just take like a snapshot of them, and they sit there. And then you've got like light particles, electrons, whizzing around on top of them, and they're seeing some disordered potential, so they get localized. And there was a lot of numerical and like theoretical work on this a few years ago. I don't think I'm that up to date on it, but my understanding is that the result of that work was that no, these systems aren't actually localized asymptotically. They do diffuse extremely slowly, on like slowly on the time scale, even of the big particles, I think. But they should also be described. Yeah.
Static. Okay. No, I mean, I just thought there were other proposals, I believe. So I'm not sure. At least for some, I believe there was a firm statement that the system remains non-ergodic arbitrarily long. But again, probably.
Yeah, I don't know which ones you're talking about.
Well, the ones, I mean, apart from, let's say the ones I know, I mean, there were proposals based on the Vanier-Stark Hamiltonians.
Sure, but those aren't translationally invariant, right? Like, of course, those are not disordered, but they are not.
Okay, yeah.
They have this linear potential.
Yeah, I'm probably confusing the disorder-free systems that are also non-ergodic. But then also, I think Roderick Massner and company, they were looking at, well, I think precisely what you're saying, but I thought they had a control and were able to show that nothing diffuses, but I might have missed that. I mean, they were looking at a system where you have two species of spins, if I remember correctly, not particles, heavy and light. But again, I mean, that's fine. I wanted just to know the idea. And another kind of question, I'm wondering whether this Jacobi tool might also be useful for glasses. This is not exactly MBL, but this is also a system that is bad at thermalizing. I wonder, perhaps quantum glasses, because that's where you would think about resonances. I wonder if you can, if it might provide a useful tool as well there.
Yeah, so that's definitely something that we have also speculated. Yeah, I mean, like people all around have been like noticing analogies between this like pre-thermal Mbl regime and glasses. To my understanding, that relationship remains imprecise. People just say, like, you know, they smell like each other, right? Like they're both bad at thermalizing. They have a lot of the same kind of similar phenomenology. I think glasses can also show this stretched exponential relaxation, or maybe it's logarithmic in glasses. It's like slightly different. But yeah,
I guess yes, the glasses definitely. I guess the problem is that spin glasses would have a proper glass phase, but then not much is known in finite dimensions. So you probably don't want to compare it to the dimensions.
Yeah. So yeah, let me like directly address your question. Like, could you use Jacobi? It's not clear to me that you could. It might depend on like the specific kind of glass that you're thinking about, but like I know a lot of these, excuse me, a lot of the dynamics in these different glasses are more kind of like you imagine them as like proceeding through like Monte Carlo updates, right? Like they're doing some gradient descent in some like messy energy landscape, which is really quite. Whereas Jacobi, like as it was originally invented, is something which is about like linear operators, right? So something we have speculated in which might work is that you might be able to do Jacobi on like the master equation, right? If there's some like Fokker-Planck kind of description of the glass, maybe you could do Jacobi on that. At that point, it might start looking a lot like the KAM procedure, in like it's more like classical setting. But yeah, like so this is all somewhat speculative. I think that maybe you could use Jacobi in that setting, but I don't know exactly how.
Yeah, well, I mean, of course, with classical glasses, I agree that's more of a gradient descent, but I think you can devise proper quantum glasses where you will be dealing with proper operators. And it's
still Hamiltonian evolution?
Yes, why not?
Yeah, then sure. Then you should be able to use Jacobi directly.
Okay. So I wonder if there are any other questions. Well, I don't see any raised hands right now. Then I guess we can thank David for his nice talk. And with this, finish the official part of the seminar. Thank you.